In our previous discussions of kinetics, we've talked about rate laws. And with the rate law, we said that the rate law indicated the impact that concentration was going to have on our rate. But when we talked about those factors that impacted rate, we said concentration was a big factor, but we also said temperature was. And so now we're going to start to take a look at how temperature impacts rate, as well as how it impacts our rate law. So concentration and temperature are the two biggest factors impacting rate. Recall that rate law examines the impact of concentration on rate. In terms of temperature, we find that all reactions speed up with temperature. In fact, it's common to see that for a 10-degree increase in temperature, we're going to find that our reaction rate doubles. So if we go back and think about what we know to be the requirements for a reaction to occur, we're asked, does that statement make sense? Does it make sense that all reactions should speed up when we increase the temperature? So remember our two requirements for reaction rates. Our particles had to collide, and they had to collide with enough energy in order to break original bonds. If we are increasing temperature, and so hopefully this statement makes sense. If we are increasing temperature, that is increasing the kinetic energy of our particles. So if we're increasing the kinetic energy of our particles, they're going to move around more. And if they can move around more, that's going to increase my collisions. Now, not only is increasing that temperature going to increase my collisions, but it also increases the energy available to break those original bonds. Now, if we saw a 10 degrees increase resulting in a doubling of our rate, if we were to cut our temperature by 10 degrees, we're going to see the rate cut in half. So with problem 2, we're asked if the temperature were lowered by 20 degrees, how would that rate, first of all, would the rate increase or decrease? So if we are lowering temperature, the rate is going to decrease. It's going to slow down. Particles don't move as much, they don't collide as much, and they have less energy to break bonds. Now, for every 10-degree change, we're going to either double or cut in half. So if we're going down 20 degrees, we're going to cut in half twice, which means we're going to be 1/4 as fast. So if temperature has such an impact on rate, why don't we see it in the rate law? Well, it's not overtly there, but we do actually see it there. Recall that the rate constant K is temperature dependent. And that K is temperature dependent based on the following equation. So we have this equation that says that K is equal to A times E to the negative EA over RT. This equation is known as the Arrhenius equation. In this equation, that EA is referred to as activation energy. T is our temperature in Kelvin. Recall from first semester chemistry to convert between Celsius and Kelvin. We take our Celsius temperature and add 273. R is our ideal gas constant. It's 8.314 joules per mole Kelvin. And then A is what we refer to as a frequency factor. It's the fraction of particles that are able to obtain enough energy. Now, an important component of this equation, and the first thing we have listed, is the activation energy. The activation energy is often described as being an energy barrier. It's the energy barrier a reaction must overcome to move from reactants to products. Now, during a reaction, reactions proceed through what is called a transition state. The transition state is a high energy species, also called an activated complex, which breaks apart to form products. So say, for example, we have the reaction of A plus BC producing AB plus C. And we'll try to draw this out more clearly. So A plus BC produces AB plus C. So to go from those reactants to products, A is going to have to form a bond with B in this formula. B's bond to C is going to have to break. So as A approaches BC, A is going to begin to form a bond to B. So here would be my bond forming. At the same time, B is going to begin breaking its bonds with C. Now there is a period of time, which is going to be this activated complex, this transition state, where both of those bonds are there. They're not quite full bonds. They're kind of in transition, hence a transition state. And this is a very unstable state. Now, this state has to be achieved in order to form products. So if A doesn't start to form a bond to B and B doesn't start to form a bond or break its bond to C, we're never going to get those products. So we have to reach this transition state in order to form our products. The activation energy is the energy required to achieve that high energy state. Activation energies can be visualized on progressive reaction curves. These curves plot energy over the progress of the reaction, or sometimes we might see time plotted. So the following curve represents an endothermic reaction. From one of these energy profiles or progressive reaction curves to another, we're going to see the same features. We're going to start off with the energy of our reactants. We're going to end with the energy of our products. We're going to see a rise in energy. We will always start off by seeing a rise in energy until we reach that activation energy. At that point, at that peak, that is where we have our transition state. So we have to absorb enough energy to reach that transition state so that activated complex can form and then proceed on to products. Now we can get some other information from these curves as well. So looking at problem number 3 in our worksheet, we're asked to look at this curve and we're asked what we notice about the difference in energy between products and reactants. So remember, along my y-axis, that's energy. Energy is increasing as we go up the y. So the product energy is higher along the y than the reactants, which means that the energy of my products here is greater than the energy of my reactants. So if that is the case, we're going to look at the change in energy. So the change in energy would be the difference in energy between my reactants and my products. So this area here, that would be my overall change in energy, the difference from where I start to where I end. So that change would be my final minus my initial. So that would be the energy of my products minus the energy of my reactants. Now, if my products are greater, so I am subtracting a smaller number from a larger number, that means that my change should result in a positive number. Now, if we say that a change is positive, that means that something is increasing. And if we're talking about energy, that means that our energy is increasing. And for a reaction, if energy is increasing, that means that energy is being absorbed. Now, we said this was representing an endothermic reaction. You should have seen some of this terminology first semester chemistry, but to recall endothermic means or when we have a positive delta E, that means we have an endothermic reaction. It means that energy is gained, it is absorbed. So from this graph, we can get our activation energy. That's the difference from our reactant to the top of that peak. At the top of that peak, that's our transition state. We can also get our total energy change. Now that total energy change, that's our enthalpy. Sometimes you'll see it delta E, sometimes you'll actually see the enthalpy. So we can get our enthalpy from our progressive reaction curves. Now, the next curve on our worksheet is representing an exothermic reaction. Now, notice that we'll see the same features. We start with the energy of our reactants, we end with the energy of our products. The difference is going to be what their energy levels are. So in this case, my reactants start higher in energy. And so what we're going to find here is that the energy of my products is less than the energy of my reactants. So my reactants start at some energy, we rise in energy until we reach that transition state, till we achieve that activation energy, and then we come down and form our products. This time the products end up with lower energy than we started with. And so again, if my energy change is the energy of my products minus the energy of my reactants, and my reactants are larger, so I'm subtracting a larger value from a smaller value, that results in a negative number. So negative here is indicating how much something decreased. So we ended up with a lower energy because we decreased or we lost energy. And if we are losing energy, energy is negative, that is indicating that overall energy is being released. So no matter what, endothermic or exothermic, we have to have energy coming in order to reach that activation energy. What's determining endo versus exothermic is the overall energy change. So if we compare where we ended to where we started, did we get a net gain or a net release of energy? So to define an exothermic reaction, this is one in which the energy change is negative and energy is released. And that occurs when our products end at a lower energy state than our reactants were at. So again, we see the same types of features, and in both graphs we've indicated an activation energy. So we've been asked in problem 11, how does our plots change with activation energies? So our endothermic graph versus our exothermic graph, they had different activation energies. And what distinguished those different activation energies was those peak heights. So if the activation energy changes, the peak height changes. Now, sometimes we talk about activation energy as being analogous to someone climbing a hill. So when we talk about it being a barrier, we compare it to someone climbing a hill. So if you think about climbing a hill, shorter hills are easier to climb than tall ones. Oh, it's going to take a lot longer to go out and climb a mountain than it is to climb a small hill. So if that's the case, we're asked, what do we think happens with activation energy? If that's a hill we have to climb and shorter ones are easier things typically occur more quickly. And so what we're going to find in terms of our activation energy is that the larger the activation energy, so the higher the hill is we have to climb, the larger that mountain is, the longer it's going to take us, the slower our rate will be. So we can compare progress of reaction curves and use them to identify which reaction might have a faster rate. So if I have a progress or reaction curve where I've got energy along my y, I have progress or time along my x, and I want to compare two different reactions. We start with the energy of our reactants. We gain energy till we reach that activation energy. And then we decrease until we reach our products. So the difference between the reactants and the peak is my activation energy. Now if I compare it to this other reaction, where I essentially have my reactants starting at about the same energy, my products ending at about the same energy, but what I'm seeing is the difference in these heights. Where if this is 1 and this is 2, the activation energy for 1 is much larger than the activation energy for 2. The larger the activation energy, the slower the rate is going to be. So with problem 13, we're asked what our faster rate would be. The smaller peak, the smaller activation energy would have the faster rate. Now, the way temperature is going to impact this, because our activation energy impacts K, which impacts our rate. Temperature, the higher the temperature our reaction occurs at, the more likely we have particles that can obtain this energy. So the more energy our particles have, the higher likelihood they can obtain that activation energy and become products. Now, the Arrhenius equation, we've looked at one form of it. We'll look later at some other forms that we can use to also determine activation energies.